All right. So on Friday, we were talking about this idea that if we have our margin of error, which is z sub alpha over 2, okay? Some textbooks are just calling it z. Some textbooks are calling it like z star. If you whatever publication you're looking at, it might make sense to look at the notation that they use and see if they have an explanation of why they use that notation. In all actuality, the alpha over 2 is just a subscript for identifying what it stands for. Does that make sense? We don't do any algebra with that alpha over 2 within these formulas. So if you just want to write it as z, that's fine. And that actually makes writing these formulas and doing the algebra a little bit easier. So I'm just going to write it as z. And then we've got times the square root of p hat q hat over n. Okay, that was the formula for finding our error when we're doing population proportions. Okay, now we talked about on Friday, I gave you the example that we ran through. I think there was 1,012 people sampled in a particular situation. And we thought, well, that's kind of an odd, bizarre number. If I'm going to sample 1,012, why not just stop at 1,000? Okay, do those 12 extra people really matter? And the answer to that is yes, they do matter. But why do they just randomly choose 2,000 or 1,012? The reason they do that is because we can set an error that we're interested in. Maybe I want a 3% error. That's kind of a hallmark that statisticians and pollsters have just gravitated towards. That 3% error is kind of the standard across statistics. Does that kind of make sense? So they say we're going to use a 3% error, and then if we know we're going to use a 3% error and we want a confidence level, and usually they choose a 95% confidence level, okay, what happens then is we can solve for n, okay? When we solve for n, okay, if I go through this process, I'm going to divide both sides by z, and that would give me the square root of p hat q hat over n. I'm going to square both sides. So when I square both sides, it'll look like this initially, but we can use a distributive property with exponents to make this e squared over z squared is then equal to p hat q hat over n. If I multiply both sides by n, it's going to give me n e squared over z squared is equal to p hat q hat. And I want to isolate n, so I'm going to multiply by the reciprocal of e squared over z squared. So I'm going to multiply by that. Those should cancel. That should cancel. Come over here. I get, multiply by the same thing over here, z squared over e squared. So what that does, it produces the formula n is equal to p hat q hat times z squared e squared. Okay? That is the formula. If we know what confidence level we want, 95% confidence, so that's going to set the z value. We want a particular margin of error, e, we're going to say is 0.03. Okay, and as we're doing study, if you want it to be 0.05, let it be 0.05. You want it to be 10%, let it be 10%. Okay, whatever you want your error to be, you can fill that in. Okay, now the p hat and the q hat, those are things that we don't know because remember, p hat and q hat, those things come from the actual sample. Does that make sense? And right now, I'm trying to determine what my sample should even look like. So I don't even know what p hat and q hat are. However, think about what they are. Okay, p hat and q hat are complements of one another, and they refer to the probability of a success and the probability of a failure, so they should total 1. Does that make sense? So these numbers can go from p hat to q hat. They can only be 0 to 1. Okay, and they're going to be complements of one another. So if we go over, I wrote it out here, it says, So we solve for n, we've done that. It says if we have no perceived or preconceived ideas about p hat, okay, meaning I have no idea what the population proportion, that point estimate, should look like, okay? If there are previous studies, I might have a preconceived idea. But if I'm the initial study, I have no idea how many people are going to maybe be in favor of their job, or what was this question was talking about, a law banning handguns, okay? I have no preconceived ideas about this, okay? So what I would do is I would let p hat be 0.5, and I would let q hat then be its complement, which is also 0.5. Does that make sense? Okay? Because what that does is it will maximize this number right here. Okay? If we go through, those of you that took college algebra, you know this. If I have x and then 1 minus x, okay, I get this formula, or get this image right here, correct? Okay. So it's a parabola. The maximum of that parabola is right there. Okay. Which means then that point, so this is p hat times q hat. Does that make sense to everybody? Okay. The maximum here is found at an x value of 0.5. Well, the x value of 0.5 is maybe the p hat. And if that's 0.5, then this would be 1 minus that, which is also 0.5. Does that make sense to everybody? Okay. If we do something like this, if I say P and then Q, and then say P times Q, do it this way, that'll work. 0 to 1, and make Q 0 to 1. Let's identify, how can I do this? There we go. Q equals 1 minus P. All right. So I've got right here a formula for P times Q, or P hat times Q hat. I'm defining P to be a number between 0 and 1, and then Q will be its complement. Okay. It's going to take this number here and multiply it by whatever this number is here. And the only way that I can, so I look at this number, I'm looking at that, that number right there, and I want to see how can I make that number the biggest it could be. Okay, well right now as I'm moving there, that number is growing, and eventually that number will start to shrink, right? Okay, so at what point was that number the largest it could have been? Would have been right there, correct? And you see that P is 0.5 and Q is also 0.5. And if I go beyond that, now I'm less than that 0.25. So that maximizes this amount. Well, why do I want that maximized? Here's the thing. If I want to guarantee a margin of error, that number needs to, if I have no preconceived ideas, that P hat times Q hat needs to be essentially an overestimate. Okay? Because it will produce a large enough N to guarantee at least a 3% error. Does that make sense? Okay. So if I only need 1,012 to generate a 3% error, it's going to be okay to have 1,050 as my sample. Does that make sense? And that's what that's going to do. If it's going to give us the bare minimum value of N that will guarantee the error that we were interested in. Okay. Now, if you have preconceived ideas about what P hat could be, maybe I've already done a study and I know P hat might be 0.6. Then I can use that. 0.6 here and 0.4 there. Okay. But if you're the initial study here, then that's the approach we're going to go. So if I'm doing that last question, okay, we said N is equal to, so I'm going to take P hat to be 0.5, Q hat to be 0.5. We wanted a 95% confidence level, so Z is going to be 1.96. And then my error, we said we wanted to be 0.03, 3%. If I square those, see what this would have generated. And I'll move that back so you can see it in a minute. So 0.5 times 0.5 times 1.96. Okay, 1.96 squared. Remember, Z is going to be squared. And we're going to divide all of that then by 0.03 squared. Okay, so I get 1,067.1. Okay, so if I'm doing this study to guarantee that I get a 3% error, I would have to capture 1,068 people. Does that make sense? You always round these up. No matter what your decimal place is, you always round up to the nearest integer. Okay? So if I had no preconceived ideas, my sample size needs to be that. Now, if you remember the problem said the sample size had to be 1,012, right? So what that tells me is that the sample of 1,012 used preconceived values for P and Q. Does that make sense? They had already an idea of what those results should be. Okay. Does that kind of make sense? Can we do that? Okay, and that formula is, it's constant all the time. Okay. If we go back to, so the next question asks us to do something using that. It says a researcher wishes to estimate with 95% confidence the proportion of people who own a home computer. So the previous study shows that 40% of those interviewed had a computer at home. So the researcher wishes to be accurate within 2% of the true population proportion. Find the minimum sample size necessary. Okay, so I'm trying to find the sample size. So I'm going to use N is equal to P hat, Q hat, Z squared over E squared. Okay, now what is E that you're going to look for here? 0.02. Okay, does it tell you what P hat should be? 0.4. And then Q hat would be what? 0.6. Okay. Now I need to find Z. So Z for our particular problem would be what? 1.96. Remember, Z attaches to the level of confidence. Okay. All we have to do then is plug that information in. So now we're looking at 0.4. 0.6, and then the denominator is going to be a 0.02. So here it would say that I need 2,305 participants to garner a 2% error. Okay, we've been asking we've been talking about how when we take samples from a population, a sample is never identical to the population, correct? Okay, so if I have, a population, let's just say that let's talk about the high school. Okay, high school, let's say we have about 450 people in the high school. Okay, if I take a sample of 10 people, is that going to be representative of the 450? The question is yes or no. Okay. And I can't really answer that. I'm not certain, okay, because there's other pieces of information that should go into that, okay. What am I interested in? What's my confidence interval? All that kind of stuff. Does that make sense? Okay. So we've been talking about how the more individuals you have in your sample, the larger your sample is, the less variability there is, correct? What we can basically do here now is define that variability. We can restrict it. Say we want 2% error. Okay. So then how big of a sample do I need? I need to take that one. Okay. In this case, 2,305. So as a researcher, before they do anything, they set these, I don't want you to get confused, but we set these parameters that govern our research and say, okay, we're going to need this many people. We want this confidence error. We want this confidence level. We want this margin of error. What does that sample then have to look like? Does that make sense? And now we can say, okay, well, now we need to go conduct surveys to generate that amount of responses. We cool with that? Okay. It says, what if you were, or this was the first study to be conducted? How would that change things? What would those two things become if I was the first person to conduct the study? They'd both be 0.5. So let's see how that changes that value. Okay, you see now, okay, what was it, 2305 before? Okay, so now we've got quite a few more that need to be incorporated into that sample simply because I have no preconceived ideas. So that would be the largest the sample needs to be. Does that make sense? Okay. So that's how. Now we can do this same thing. If you remember when we talked about means. Okay, let's go back to 8.2 when we had this formula here. Okay, can I and it be the same thing with z's in 8.1? This formula here. Okay, can I, if I just look at that one or at that portion right there, can we go through, because that's my error, can I go through and solve for n there? Does that kind of make sense? That's a different formula, maybe a different, you would divide both sides by z, then you would multiply maybe both sides by a radical n, try to isolate. So it would be, at the end, a different formula to find my sample size, but each of these can allow you to decide how big of a sample should we take so that we can narrow down to a defined or a preferred margin of error instead of just taking samples of unknown sizes or random sizes and hoping for maybe a small margin of error. Does that make sense? Okay. Also, it allows researchers to, be frugal, okay, or conservative with their resources, meaning every researcher is going to have to put money towards surveys. They might have to hire people to go conduct these surveys. They'll have to have maybe hire somebody to create the survey. If I can minimize the amount of people I have to produce this survey for, that's going to save me money. Does that make sense? If I only need 2,000 surveys per one of these formulas, and I didn't use this formula, I go print 4,000 surveys, I'm going to have a less margin of error, but if it wasn't necessary, I've wasted a lot of money. Does that make sense? Okay. So those are all things that are done prior to actually acquiring the data. All right, that's where I was going to stop today with you guys. Do you have, so that concludes 8.3, talking about proportion populations, or I guess population proportions. Does anybody have questions on this stuff? My hope is that you're starting to see, once we did z-scores and t-scores for sigma being known or unknown, that as we go through these other confidence intervals, it's really the same stuff, right? Okay, we just have to decide, what are we talking about? We're talking about, a known standard deviation, population standard deviation, unknown standard deviation of the population. Or in this case, are we talking about proportions? Okay. Tomorrow we're going to start chi-squared. Okay, which chi-squared starts to investigate variances and standard deviations. Okay. And it's really a similar thing. Now it's a new distribution, it's a new table. But if we understood what we've been doing, it should be an easy transition once I teach you how to use the table. And I'll look into whether there's technology that we can use as well, software that we can use to get the values from the chi-square distribution as well. I think Excel probably has something built into it. It's a little bit of the table's messier. The chi-square distribution is not symmetric, so we can't. If I if we get a z-score of 1.96, we know that's a negative 1.96 and a positive 1.96. Chi-square's asymmetrical, okay? So that'll be an issue with the technology, I think. But I'll see if I can figure it out. But once we have those pieces of data that go into the formulas, then it's the same exact thing that we've been doing here, okay? When we get into the following section, 8.5, that talks about the difference between two sample means. Okay, so we'll see, okay, how does this class's average compare to maybe 7th period's average? Okay, and the difference will be the thing that we look at there to do a confidence interval. But once we do that little portion, everything then kind of comes back to what we've been doing in 8.1, 8.2, and 8.3. Okay, so that's the plan as we move forward in the next couple of days. There isn't, like 8.3 I said is available still on Math Excel. If you have not finished that, I would maybe start working on that now, finish that up for tomorrow.